A single second of uncompressed stereo audio sampled at 44.1 kHz with 16-bit depth generates 176,400 bytes of data. Storing a 3-minute song requires over 30 megabytes. This massive data rate, defined by the Nyquist-Shannon sampling theorem, necessitates efficient reduction. The raw audio signal exists in the time domain, representing amplitude fluctuations over time. Compression algorithms cannot efficiently analyze redundancy in this domain. We must shift perspective using spectral analysis, decomposing the complex waveform into its constituent sine and cosine waves. This transformation reveals the underlying frequencies and their respective amplitudes, which is the fundamental purpose of the Fourier transform. The Fourier transform is an integral operator that maps a function from the time domain to the frequency domain. Mathematically, the continuous Fourier transform of a function f of t is defined by the integral from negative infinity to positive infinity of f of t multiplied by the complex exponential e to the power of negative I omega t, integrated with respect to t. This integral represents the accumulation of the signal's correlation with every possible frequency component omega. The complex exponential acts as a rotating phasor, and the integration accumulates the total overlap. This process is fundamentally rooted in the calculus concept of accumulation, where the limit of Riemann sums defines the area under the curve, quantifying the total contribution of each frequency across the entire timespan. Digital audio signals are discrete, requiring the Discrete Fourier Transform, or DFT. The DFT replaces the continuous integral with a finite summation over n samples. Calculating the DFT directly involves n-squared operations, making it computationally prohibitive for real-time processing. The Fast Fourier Transform, or FFT, is an optimized algorithm that exploits the symmetry and periodicity of the complex exponential terms, reducing the computational complexity to n log n. The FFT is the essential engine enabling rapid spectral analysis within the MP3 encoder, allowing the system to analyze short, overlapping frames of audio data, typically 1024 or 576 samples, to maintain temporal resolution.
Lossy compression relies entirely on psychoacoustics, the study of how humans perceive sound. The critical insight is auditory masking. If a loud tone, the masker, is present at a specific frequency, the human ear cannot perceive quieter tones, the maskees, within a narrow frequency band surrounding the masker. This phenomenon is frequency-dependent, meaning the masking threshold varies across the spectrum. The MP3 encoder uses a perceptual model based on the FFT output to calculate this precise masking threshold for each frame. Any spectral component falling below this threshold is perceptually irrelevant and can be discarded or heavily reduced without audible degradation. Before applying the FFT, the audio stream is processed by a filter bank. The MP3 standard, specifically MPEG-1 Audio Layer 3, uses a hybrid filter bank structure. It first employs a Polyphase Quadrature Filter bank, or PQF, which splits the audio into 32 equally spaced frequency subbands. This initial filtering provides coarse frequency resolution. The subsequent application of the Modified Discrete Cosine Transform, or MDCT, within each subband provides the necessary fine spectral resolution required for accurate masking calculations. The MDCT is closely related to the Fourier transform, but uses real numbers and overlapping windows to minimize artifacts at the frame boundaries. Quantization is the process of reducing the precision of the spectral coefficients. Based on the masking threshold calculated in the psychoacoustic model, the encoder determines how many bits are necessary to represent the amplitude of each frequency component. Components significantly above the masking threshold receive more bits, ensuring high fidelity. Components near or below the threshold receive fewer bits or 0 bits, effectively discarding them. This non-uniform quantization is the primary source of data reduction in MP3. The encoder iteratively adjusts the quantization step size until the resulting noise, known as quantization noise, remains below the calculated perceptual masking threshold for that specific audio frame.
After the spectral coefficients have been quantized, they are still represented by numerical values. The final stage of the MP3 compression pipeline involves entropy encoding, specifically Huffman coding. Huffman coding is a lossless compression technique that assigns shorter bit strings to frequently occurring quantized values and longer bit strings to less frequent values. This exploits the statistical redundancy remaining in the data stream. While the psychoacoustic model achieved the massive lossy reduction, Huffman coding provides an additional 10 to 20% reduction without losing any further information, optimizing the final bit stream structure. To play the compressed file, the decoder reverses the process. It first decodes the Huffman stream, then dequantizes the spectral coefficients, and finally uses the inverse Modified Discrete Cosine Transform, or MDCT, combined with the inverse Polyphase Quadrature Filter bank to reconstruct the time domain signal. The inherent limitation of lossy compression is the introduction of artifacts. If the bitrate is too low, the quantization noise exceeds the masking threshold, resulting in audible distortions like pre-echo, where quantization noise becomes audible just before a sharp transient sound, or spectral holes, where too many frequency components were aggressively discarded. The efficiency of MP3 is measured by its bitrate, typically ranging from 96 kilobits per second to 320 kilobits per second for stereo audio. A standard 128 kilobits per second MP3 achieves a compression ratio of approximately 11 to 1 compared to the original CD audio, reducing the data rate from 1,411 kilobits per second. This massive reduction, driven by the Fourier transform's ability to isolate perceptually irrelevant data, fundamentally changed digital media distribution. The FT remains the core mathematical tool across all modern perceptual codecs, including AAC and Opus, demonstrating the enduring power of spectral decomposition rooted in integral calculus.